Good afternoon to everybody. So today we will be starting the very first lecture of the topic time domain analysis of first and second order system. So we will start with saying how do you define first and second order system. In fact, what actually you mean by the first and second order system. How do you obtain them, and why do we need them? And finally, why do we do the time domain analysis? What purposes? Okay. So this will be the content for this topic. We'll start with a brief introduction about the transfer function, state space models, and the relationship between these models. Then we will study the standard process inputs, that what inputs do we use to the time domain analysis. Then we see what are their responses on the first order system, integrating systems, second order systems, and also we will see the effect of poles and zeros, how the poles and zeros of a transfer function affect the system response. In addition, we will also see the time delays, system with time delays, and finally, we will conclude with uh, defining the higher order transfer functions and why do we need to approximate them to lower order systems. We'll learn after this the whole topic, what you will take away with this topic. So you will going to understand the inherent dynamic behavior of the system by itself. That is to say that we won't be including any controller or any interference from the controller. Whatever we are going to study is the open loop. Okay. The second thing is by how much and in what manner the plant responds to a change in the input variable. Okay. So what we aim to see that we apply an input to an open loop plant and how much the output or the response of the system will going to change and in what manner. Okay. The concept of representing plant behavior with purely mathematical expressions. Okay. The dynamic behavior of low order systems, higher order systems, including the inverse response and the time delay system. And finally, how you could approximate the higher order systems to lower order systems. So these are the references material for this whole topic. There are two books, in fact. So one book can be used as a textbook, and another book is just for the reference if you want to go a bit deep into the material. Okay. So now coming or starting with this time domain analysis for the first and second order systems. So let's say if you, since you must be belonging as a from the electrical engineering, okay. So let's say if you visit a factory or a automation plant, so this is the kind of plant you see there, okay. Then you need to identify, okay, what are all the sub processes that you need to concentrate on to do the proper control. Okay, this is the whole setup or a very complex setup where you would see some reactor module where the some mixing of the raw material is done so that we could have the product quality according to the desired specification. Okay, this is a separate thing where we take into account the role of the controller. But here, if we just want to see the process, to study the process, and to see the dynamics, so that we can design finally the controller. Okay, so here in this very first example, you need to identify the sub process where where it is critical in the sense to study the dynamics. So here you could identify the very first sub process called the reactor, which is highlighted in red color. Okay. So let's say if we concentrate on this reactor, we'll see into the next slide. Okay, so this is also called a blending process where the mixing of either 2 or 3 material is done so that we can have the possible or desired outcome, whatever we want. So let's say and this is on the right hand side, we need to mix these 2 materials so that we can have the desired specifications on the X and W. Okay, so this is a process for us. And if I ask you, either it is a first order system or a second order system. So what you can do, you can write your answers in the chat, okay, and then I would see if you are going in the right direction or not. So for this process, we need to first of all model this process considering the energy and mass balances so that we could finally identify whether it is a first order system or a second order system. So let's see how do we model the system and what do we exactly mean by the model. Okay, so now let's say we will do the energy balances. So we'll start with the mass balance. I will call it the unsteady state. Okay, so what do we need to have? How much mass is accumulated in the tank and the rate of mass in and out. Okay, so considering the dynamics, so we have this x1 w1 x2 w2 and the volume of the tank is v, and finally we have the outcome x and w. Okay, so if I write the differential equation for this above equation, I would have, okay, this is the first equation, this is the mass balance. Now the second comes the component balance. This is also at unsteady state. This equation will be, this is my second equation. Okay, now what we assume here, suppose rho and v are constant. So if I expand these two equations, go to this first one, okay, this will be rho dv by dt. Take the two equations. Okay. So what simplify more further, what you can do, put the third equation into this fourth equation, and finally you will get or the simplification of the very first one. So now we will proceed further with this main equation. This would be our main equation, which will define what is exactly the model and what is the order of the system. So let me write again this equation so that we could proceed further. Okay. So now we will make some assumptions on this process to see or to simplify the process in the sense that we could have a linear system. Okay, so I think there are some issues with the battery. Okay, so we were here with this equation. Now I will make some assumptions in the sense. So since we are considering the material A and B, that both the feed and outflow composition of A are dilute, and we have the components x1 of A and x of the output. Since x1 and x2 are matching to give the x, and if based on this assumption, we will have x1 is less than x, which is much more less than 1. If we have a pure A, in that sense, for pure A, I would have x is equal to 1. Okay. Second assumption is W1 is constant. It is the weight. So I will denote this by a different variable. So this bar symbol denotes that it's a constant quantity. And see that the stream 2 is pure A. That is x2 is equal to 1. Okay. Now based on this assumption, I will proceed with the above equation and we'll see the steady state component balance, which is equivalent to say that I am putting dx by dt is equal to 0 in the last equation. So I will have 0. Okay. So now coming back using that assumption, I will have from the first that if x1 is less than x less than 1, this implies that w2 is very less than w. Okay. So with this assumption, what I would have, now think on this equation, that if the w2 component is very less than w, where w is the final product or the weight of the final product, and w2 is the weight of the stream 2. So this means to say that whatever the w I am having is almost coming from w1, and w1 is what is constant for us. This is what our assumption, the second assumption. Okay. So now if I simplify this equation on this first node point, what I would have 0 w bar x1 bar, because w1 is almost equivalent to w, and if I come for this second term or the last term, I would have only w2 bar, because here we have x2 component and x2 is equal to 1 already with that assumption. And finally I would have w bar x bar, and see from this one that w2 is already less than w bar, so I would have w bar x1. Okay. So similarly, if I use the same assumptions in this equation, I would have note that the bar symbol denotes the constant quantity, So now I have three variables: x, which is the output, x1 and w2. x1 and w2 are the inputs to the system. Okay, so I need to have some kind of model or a simple representation in terms of transfer function, so that I can map these inputs to the output. Since these are the differential equations, I need also to consider the initial steady state points. So if I subtract the initial steady state conditions from the last equation, I can do this easily, because dx bar dt would be equal to 0. Okay, so now if I consider them as the deviation variable, let's say x1 dash, this is w2 dash, I would have the differential equation as, okay. Now simplifying further this equation, I could write this as tau, and this one as k. Okay, and then take the Laplace transform. Okay, after taking the Laplace transform, I would have x dash s, okay. So this is the these, and these are the inputs, and this is the output. So now I have successfully figured out the model of the system. So I could denote this as G1S, and this one is G2 of S. Okay, so you see what you have understood from this, what we have done. We have a physical process, okay, and we have tried to study the dynamics of the system. We need some kind of representation, a mathematical representation of the physical process. Okay, compute the transfer function of the model, and this is what I mean the first order system, because the denominator have only one power of s, the maximum power of s. So this is here you will see that we have a linear system already. And why we have this linear system? Because of the assumptions we make previously. Suppose if we won't have this assumptions, then the system would be highly nonlinear because of the multiples w1 of x1, the nonlinearities. The nonlinearities includes or appears in the system because of the multiplying factor w1 x1. You see, so what you can do, either you could linearize the system around a specific operating point, and the best way or the one of the possible way to linearize is doing the Taylor expansion. So in that case, we would have the system like a function of x, x1. This is a nonlinear system. Okay, so we won't be proceeding with the non with this linearizing the system. So now we know that this blending process is a first order system, and we need to study the dynamics. How would we study, or let's before moving on to the dynamics time domain analysis, we also see how do you define a second order system. So let's say if you have a tank or a reactor in a cascaded fashion, so that either they interact or they do not interact. So if we have a two tank in series, okay, this will give you always a second order system in this sense, where this is the input, this one, and this is the output. What we want to maintain the height. Okay, this is the outflow. This one, Q1. There is a relationship between Q Q1 and H2, which is defined by this transfer function. This is also a first order system. Okay, and finally I have a relationship for this valve between the H2 and Q2, which is just a constant. So if I put all this transfer function in series, I will have a second order system. Okay, so I could write over here the system I would have from Q2 dash S by. Okay, let me write onto this on the P node, on the one node. So here you will see the maximum power of S is 2. This is what we call the second order system. So what we have seen so far, we have modeled the system in a transfer function domain. So there are some interrelationship between the model forms, or let's say we could model the system in many different ways. Either we have a transfer functions, either we have an impulse response, which is based on the experimental data record in a state space form or the frequency response form. So there must be some interrelationship between all the system. And the relationship is, if you have an impulse response of the system function, you could take the Laplace transform and finally you would have the transfer function. And if you take the convolution integral of the transfer function, you would get the impulse response. Okay. So this is the relationship between the transfer function and the state space that you need to realize. What do you understand by realization? That you need to identify the dynamics of the differential equation of the state basically. Similarly, we have the relationship between the impulse response state space, where the impulse response is you get by having an analytical solution of the state space system, and this is defines you the x variable. So these are all the relationship between the representation of the system, and you could use any representation to study the dynamics, the time domain dynamics. In this topic, I will cover only this transfer function, using the transfer function, that how you could use a transfer function to do the time domain analysis. Okay, now coming on to the dynamic behavior, what do we want to do? We would like to investigate how processes respond to typical changes in the environment, and by meaning the changes in the environment are the inputs. Either these are the manual inputs which we can manipulate, or either there are some disturbances, or which we classify them, or some variables which we classify as the disturbance variable which cannot be manipulated. These are also called the free variables. So if we are able to identify or determine the response of the system based on these two variables, then we can design our control system. So the very first standard process input comes the step input. So in industry, processes are very subjected to sudden and sustained input changes. You have a material or the inflow of the material into the reactor, and suddenly there's a step change in the material which you need to tackle with your controller by a controller. So if I see that how the step input looks like, this is how you mathematically define the step input. You have the value 0 for the time t less than 0, and you have some constant, let's say m, for t greater than equal to 0. So if you take the Laplace transform, you would have u of s as m by s. Okay, and this is how you could model in your MATLAB with this very simple basic code. So if you have a MATLAB installed in your computer already, you could run this code, see if you are getting a step signal. The second input is the rectangular pulse input. So this input is basically, you see, it starts with 0, it stays there for that constant value, and suddenly it come back to its original value, or either set some value. So for example, a feed to the reactor is shut off for a certain period of time, or a natural gas fired furnace experiences a brief interruption in fuel gases. So in that case, you see this kind of behavior to the input of the process. And if I write the mathematics of this signal with rectangular pulse t 0 for t less than 0, some constant value h, also you could denote this signal with the help of step response, because you see, if I represent the rectangular response, it is this one. Okay, so how I could um, represent this signal using the step response? So if I have this signal, let's say this is the step signal, and if I add the same value, okay, then you would get this signal. So if I represent it mathematically, it will come. If I take the same denotation, so this and this are the step signals. In taking the Laplace transform, I would have, okay. Also, another important signal is the ramp input. The ramp input has this kind of behavior where it starts at 0. Either it gradually increases or decreases, depends on the process conditions. And this is how you represent mathematically the ramp input signal. You have this u of rt. So this simply means that until this point we have the 0, and afterward it increases with time t in a linear way with the slope of a. So now if I since of the above signal, it will give me this thing. Another one is the sinusoidal input. Sinusoidal input is a very input signal which you could use to study the dynamics, because since first of all it is periodic in nature, also it can be considered as a disturbance, or you can also model your disturbance variable in form of sinusoidal input. And, and notice one thing, that constantly excites the system in both ways. So I would have the basic equation for the sinusoidal input. We have the 0 for t less than 0 and a sine omega t for t greater than equal to 0. With the Laplace of this, we also study another important signal called the triangular pulse, which I'm going to use to see how the system responds to this triangular pulse. And note one thing, I could model the triangular pulse using the ramp inputs only. So let's say I have this ramp input. At some point, I have this ramp input again. And finally this one. So if I combine all these things, I would have this signal. Where if I keep this dw time. So if we try to investigate into the how this can be represented, I would write directly the transfer function of this triangular pulse. Would be so we also have another class of process input called the random inputs. These are basically the disturbance signals. So for this, for to study all this random inputs, we need to study the statistical theory to do the characterization. So we will not be going into the time domain analysis with respect to these inputs. Okay. Now coming on to the step response of first order systems, we have studied so far that how do you model the first order system, or basically from where do you obtain this. We have seen how a step signal looks like. So now what I want to say, if I have this first order system, I apply a step input, then how the system will going to behave. Let's say I put this y, I put this u. So now we'll be moving into the response of processes. So far until this position, do we have any doubts or queries? Because we have already finished with the basics and we are moving into the detailed analysis of how the signals behaves with respect to the system. Or shall I continue? Okay. So now I will move into response of I present my system in the transfer function form as a fraction of output and input. where this defines the process gain and this is the time constant. Okay, this is the output and this is the input. So this is my first order system. Now see the step response. We have seen the transfer function of the step response is represented by m of m by s. So if I put this us in the last equation, I would have y of s. Okay, which I could do the partial fraction, and finally I would have. Now if I take the inverse Laplace transform of this above equation, I would have a representation of the time domain signal is equivalent to Km 1 minus. Okay, if I start drawing this figure, I would have the yt. This is my the value of the maximum value. If I see the normalized, okay, this would be p by tau. So this is what you get if you apply a step input. First order system. You see, for the first order system, the process output does not behave all of a sudden. It reaches to the final value exponentially. And this is the very basic property of a linear system, that if you have a linear system, the growth or the decay of the output signal will follow the exponential behavior. Okay, so while studying the step response, there's another quantity which we also study. It's called the measure of reluctance. Okay, and this is defined by, so if I put the value of yt into this equation, I would have, this is the final value. Okay, so in solving this, I would get So this is the reluctance area, what we call the reluctance area. Okay, and these are few characteristics of the first order process. So what we have seen by computing that the output yt attains the value of km at steady state, where k is the steady state gain of the system. So also at when t is equal to tau, okay, when t is equal to tau, I would have this value, okay, this is 1 when t is equal to tau, and this gives me 0.632 value, the maximum value, okay. And the slope of the step response at the origin is given by this equation, which is basically the differential of the output signal at t is equal to 0. So time constants plays a very unique role in the first order system. So if you have a slow process, this is the final value and this is the output yt, let's say. So let's say I draw the two output signals for the step response. Can someone tell me the relationship between the tau 1 and tau 2? And these tau 1 and tau 2 are the time constants. So if we have a slow process, for the slow process we have a larger time constant. So this is what is represented by here. So here the k is a measure of by how much the step change in the input, and the steady state gain is given by this equation, where y infinity is the final value divided by the m, which is the magnitude of the unit step signal, and tau is a measure of how fast the process responds to the input. For the slow process, we have a large time constant. For the fast process, we have a small time constant. And the time constant is given by this relationship. Okay. Now we will see how a rectangular pulse gives the response of the first order system. So we have, okay. So recall that the transfer function of the rectangular pulse was denoted by h of s. So if I put this u of s in the first order transfer function, I would have, or in this one, we call it very quickly. I forgot the minus sign. Okay. So again, I will take the partial fraction and then the Laplace inverse, so that I could have the time domain representation of the signal yt. This is how I can do. Okay. So notice this, that I have a signal like in this way, is 0. So even without computing the analytical expression, if I ask you to write or to draw the figure, how it could be drawn? Because rectangular pulse is nothing but just the combination of a two unit step signals. Okay. So the process will stay to 0. It will rise because there is a step input for the system. It will rise to some value, and afterward it again gradually decreases or exponentially decreases. So I need to compute the analytical expression to have this final value. So taking that Laplace transform, inverse Laplace transform, I would have for t less than tw, this time window, and this for tw. It could be a exponentially rise of the signal for this until this point, and for t greater than tw, I would have, so the final value would be. Next comes the impulse response. of the first order processes or systems. Until this point, do we have any queries or doubts? Okay, try to fix the problem at your side. So proceeding further with the impulse response of first order system. So the impulse response is pretty much straightforward. We have an input which is a direct delta function with area A and represented by A of delta t. So if I take the Laplace transform of this signal, I would get U is equal to A. Okay, these impulse responses are pretty much interesting signals in the process industry because we have this kind of pulse as some input or a chain of impulse which can severely affect the performance of the system. So let's say if we consider only one, okay, of area A times 0 t. So I could write the transfer function of the output tau is okay. The impulse is the Laplace inverse response of the system is pretty much forward. I would have yt is equal to ak of tau e to the power minus t by tau. So the output will have a shape. Now even without solving, or you could plot the output signal of this system that until this point, let's say denote this 0, until this point it will stay 0. It will sh- sharply increase and finally goes to come back to 0 again with exponential behavior. So we also have a relationship between the step response and the impulse response, that if you differentiate the step response of the first order system, you would get the impulse response. So basically, if you see again the impulse input, it basically denotes a jump, and the jump discontinuity. There's a term called jump discontinuity, is very crucial in the study of control system. But we won't address those issues, or the jump discontinuity. But it's a jump signal for which we want to see how the response of the system will going to behave. What do you mean by YTH, TECTN? You can think of the second question, how you could proceed to solve. Okay, the system consider a first order system. Okay, try to read this question, study, and see if you could proceed solving this question. And okay, so I have a question that what is the difference between the step and rectangular in terms of application? In terms of application, okay, let me go back to the to this document. So if we recall that we have a step input, okay, or correctly, okay, I have a step input. and this is the rectangular input. U step, U rectangular. Okay. So basically, we experience this kind of signals. Let's talk about the process industries. Okay, where we work with the chemicals. Okay, we have a process, or let's say the example we considered in the beginning of the reactor of a blending process. Okay, I have an input. So this input, this U of ST, denotes that I have a constant supply of variable of one of the input variable into the system. Okay, but for the rectangular one, it denotes that I have a constant supply of one input until certain time. Towards I stop putting this material into the reactor. Okay, there could be many number of times we have. Let's say we have a. If I move back again to the slides, you upload the slides. Okay, so here one of the example is written from the process that a feed to the reactor cut off for a certain period of time, or a natural gas fired furnace experiences a brief interruption in fuel gas. So this denotes that until this point I have a continuous supply. Afterwards it was shut off for some unknown reason, or maybe some known reasons. Okay. Okay. So now how many of you have are able to approach that problem, or how many of you have not yet understood that what has been asked into the problem? Okay. So it says a heated process is used to heat a semiconductor wafer. Okay, a heated process is used to heat a semiconductor wafer, operates with first order dynamics. Okay, here you have already been given a first order, that the process is a first order system, and there is a relationship between the changes in temperature to the change in heater input. The heater input is given in kilowatts with the process. So the transfer function is given by k over tau s plus 1. Okay, and it also says the process is at steady state when an engineer changes the power input stepwise. Note that we have a stepwise input which changes from initial value of 1 to 1.5. So the difference or the magnitude of the step signal is only 0.5, because initially we were making a step change from 0 to the level m. Okay. Now the engineer notes the following. The process temperature initially is 80 degrees centigrade. So we now know the initial value, and 4 minutes after changing the power input, which is varying stepwise, the temperature is 230 degrees centigrade. Okay, and after 30 minutes later the temperature is 280 degrees centigrade. So here we assume that in 30 minutes the process has already reached to its steady state. Okay, now we want to find out what are k and tau in the process transfer function. You could write either in the chat or raise the compute this km is generally given by y of infinity minus y of 0. I know the value of of uh, 80, and y of 0 is 80. So I get 200, the value of km. Okay. So now I know that m is 0.5 because it makes a transition 0, 1, 1.5. So this m is 0.5. Okay. I can compute the value of k, and this is 400. Okay. Now I had its transfer function k over tau is plus 1. Now I know k. The only thing needs to find is this tau. Now how I can compute the tau? By using the information, by using this information given in the second point. That 4 minutes after changing the power input, the temperature is 230 degrees. So according to the question, it says at T is equal to 4, I have Y of 4 at 230 degree centigrade. Best thing what I could do using these two values and the same equation, and this T is basically 4. Okay. From here I can now compute the value of tau, which will come out 2.9. So now I could represent my transfer function a, what was k, 400. Okay, so this is my transfer function based on the information received by the engineer in that problem. Have you seen the computation part or it was missed? Okay. Any doubts in this problem 2a? Okay. Now the second B part asks if at another time the engineer changes the power input linearly at a rate of 0.5 kilowatt per minute, what can you say about the maximum rate of change process temperature? So now the value of A is given to you, which is 0.5, the slope. And you can use the same expression what we have computed in the lecture notes, that what is the maximum rate of change process temperature and when will it occur and how large will it be. Okay. So I will rest this B part for you to solve by yourself, and we could proceed further because we have not yet, or let okay, uh, this lecture. Okay, so the ramp response of first order system, so that you will be able to be part of that assignment. So now recalling that the transfer function of the response is by a square. If I put this u of s into that first order transfer function formula, I will get y of s, and partial fraction I would get. Now if I take the Laplace inverse of this above equation, I will get this one. Okay. So if I draw this thing, this is t. Okay. And this is my step response. Sorry, the ramp signal. So the response would look like this. Okay. It will be a bit delayed, the slope having at this point. Okay. Okay. So there are some crucial points to be noted for the ramp response. That as t tends to infinity, yt tends to this ak t minus tau value, and as we have seen in the figure, it's basically an asymptote. So there's also a relationship between the ramp response and the step response, that if you differentiate the ramp response, you will get the step response. So what has been shown to you in the figure, that there is no time limit has been given to ramp signal. Okay, generally this is not physical, because in practice it is not feasible, because once you give a ramp, or once there is a ramp signal the process, okay, the output of the process saturates at some point because of the safety issues, okay, which do not allow the output of the process to grow unboundedly in the sense that the here y of t will reach to infinity at some point, okay, and the process input frequently will be ramped from one value to another in a fixed amount of time so as to avoid sudden change associated with the step change, okay, and ramp inputs of this type are particularly useful during the startup of a continuous process. Why? Can you can you think of any reason that why it is generally useful during the startup of the process? Now think, to start a process, either we need a step kind of input, okay, that I am at t is equal to 0, I am at 0 level, and suddenly I write system to a value, let's say h, okay, and another one is a ramp input, or let's say I will give a time limited ramp input, okay, afterwards another ramp input would follow if requires. So considering the safety issues, I cannot, let's say I have a furnace, okay, where the temperature of the furnace needs to go from 0 degree to 500 degree. I cannot increase. I cannot increase the temperature from 0 to 500 degrees centigrade all of a sudden. I need to slowly excite the system in a ramp fashion so that it reaches to a 500 value. Afterwards, then okay, it could stay there for a longer time. Okay. So for this reason, generally we require this ramp input at the for the startup of the process. So possibly we could stop it here at the ramp response, and in the next session we will see some the rest of the responses, and also we will see the second order system and the integrating processes. Okay, so from the next time I would expect that the user to be more active in solving the questions, and if you still have any doubts or questions, you could write here in the chat window or in the question tab. Okay, so we'll wait a couple of minutes, let's say 2 minutes, and after this we will close the session for today's session.